Hi, I'm Alan, and I'm going to present work titled Within Task Preference Elicitation in Net Benefit Planning. This is work carried out at Heriot-Watt University with Bart Craenen and Petrick, and is funded by the Start Making Sense and Orca projects. So in this tour guide scenario, there's a user and a robot, and the robot is going to select some activities for the user to do. For example, cycling around a lake or visiting the whiskey distillery. And the utility of selecting those goals or doing those activities depends on the user. So in this case, we've got pink jumpers and blue jumpers. And so this kind of problem has been looked at in planning typically as a pre-process where you have a preference elicitation process in advance of planning. Another option is to generate a selection of plans and allow the user to select, or as an iterative process where we plan, ask the user for feedback, constraints perhaps, and then plan again until the user is happy. In this work, we're going to consider preference elicitation within the task. So, as part of planning and execution. So in this case, the robot knows that the users are either pink or blue, and they have these utility models, as you can see. So, for example, the cycle is preferred by blue, whereas the whiskey distillery is preferred by the pink jumpers. And so the robot's going to pick which activities based on the user. However, at the start of, during planning and at the start of execution, they don't know which type of user they have. So part of the problem is to find that out during the execution. And so the idea is to generate a plan like we've got at the bottom, where you have these questions or observations that the robot's making about the user, and that is going to reduce their uncertainty about which type of person they are interacting with. So we're going to set this problem as a partially observable and net benefit problem, and the idea is to get from the partially observable side we get some kind of partial state where we know, for example, in this example, that the user is at the park, but we don't know what they like. Do they like outdoors? We don't know. Also, we'll get some sensing actions. So, for example, that you can ask them whether they like outdoors activities. Potentially, you would only want to do that in certain circumstances, or you can observe them in the museum and see if they seem to like that kind of thing. From the net benefit side, we get a collection of optional goals and a kind of optimization problem of maximizing a utility minus cost term. And in this case, we have utility terms for each of the different user types. Okay, so the solution is a branching plan which branches over the different possible values of each of the user attributes when it's selected to by the planner. And the idea is that the planner decides which questions or which observations to make and when it's important. And of course they can kind of balance between what's the utility gain and what's the elicitation cost. And we've kind of achieved this by structuring the model into three parts. The first part is the task part, so you have kind of normal task actions moving around the map. You have elicitation, queries, observations, in this case likes, X, whatever, and you branch on those. And then you've got two sections that are modelling artifacts, so you've got a finish elicitation where you just ask all the questions you haven't got answers to yet, and then you sum the utility based on the full set of user attributes, and these two sections at the end are simply so that the planner is forced to think that you will know which user you had, so it has to decide whether it's worth eliciting or not during the task part. Okay. So a key aspect in modelling this is capturing multi-user preferences, and this is going to rely on two things: the agent attributes and the user attributes. So the agent attributes are the goals that the agent can choose to achieve or not. So, for example, visiting the pub. And the user attributes can't be modified by the agent, but they can be observed. Okay, so for example, that the pink jumper likes socializing but doesn't like education, for example. And as part of this, we're going to assume that the attributes distinguish users with different user preferences. Okay. So the idea here is that you then define the utility of each of the goals using both sets of attributes. So for example, if the agent picks to go to the chateau and the user likes educational activities, then you'll get 50 utility, okay. And if they don't like educational activities, then it'll only be worth 10, and if they never went, then it would be 0, okay. And the idea is that the total utility of a plan is defined for a particular set of user attribute values as the sum over each of these utility terms for all of the goals. So if we consider another example, and for example, just consider what happens for the pink jumper during execution. So if we're using a default plan where elicitation isn't possible, then the plan might have, for example, here the whiskey distillery and the pub, because they're pretty good on average for both types. A pre-elicited plan, so in this case the plan was generated in the knowledge that it was for a pink jumper, might choose the pub and the chateau because the chateau is the best, and the pub's the second best activity. And then in our case, it might choose to go to the whiskey distillery and elicit whether they like educational activities from that, and if they do, then go on to the chateau. Okay, and there's a summary table showing essentially what you'd expect. The default is the weakest, the least specialised for the pink jumper. The pre-elicit is the most specialised, has the highest utility, and our approach is in between. Okay. So our system uses an optimistic approach based on K-replanner, and it's been extended for the cost-sensitive setting. And we're using Llama 11 with no access to any elicitation as the baseline, and Llama 11 is also the underlying planner for our K-replanner extension. Testing it on 4 domains, so one inspired by our tour guide scenario, one looking at instruction giving in the briefcase domain, one with an interested operator in the rovers domain, so they, for example, prefer rock samples, and bartender scenario where the agent can pick to give a cocktail or not, and the user has preferences over ingredients. We've got constrained versions where elicitation is constrained and unconstrained when it is not. So here's the table of results showing the reduction in cost against the baseline, and the constrained versions are above the dotted line. So our approach discovers better plans in the baseline in each of the test domains, roughly 5 to 10% in each domain. The plans improve from the baseline for each of the user attribute variations, so each of the potential users that we've looked at. The approach is more effective with less constrained elicitation, so this is as you'd expect. So if you can elicit earlier, then you can specialise more. In conclusion, our approach discovers better plans in the baseline in each of the tested domains. It provides a new approach for specialising plan-based agent behaviour, which is particularly suited to situations where upfront elicitation is not appropriate, Generalized additive utility models provide a concise method of representing preference models. This is the way we actually model preferences. You can see in the paper. Our future work is to apply to a real scenario and to look at opportunities for using different planning approaches. Okay, thank you.